looking at the specific differential equation where the derivative is equal to some function of y. So of the form dy dx is some function of y. Obviously we can separate this quite easily. We'll end up with the integral of dx is equal to the integral of dy over that function of y. They are first order linear differential equations because I could rearrange it and it would end up like that. Dy dx minus some function of y is equal to some function of x. Function of x just turns out to be 0 in this case. So something like this. Dy dx is equal to a constant y minus n. We have an initial condition there of n plus a. So whenever x is 0, we get n plus a. Separating our variables, we have dy over y minus n is equal to some constant times dx. So integrating that, we get the log of y minus n is equal to kx. Substitute in. Now we want to make y the subject of all this. So e to the power of kx will be the absolute value of y minus n on a, which means y minus n will equal ae to the kx. Y ends up being that. What that actually is what we've seen already. That's just our modified growth and decay equation that we saw last year. How about this one? Dy dx is e to the power of 2y minus 1. Separate it out, we'll get e to the 1 minus 2y dy is integral of dx. And here's our final answer. Why is it different? I'll tell you why it's different. Because the right hand side's function of y instead of function of x. So it's not simply just integrating the exponential straight away. We've got to separate the variables and away we go. Square root of 1 minus y squared. Ooh, dy over root 1 minus y squared. What's that one? Is that inverse trig, isn't it? Inverse trig, yeah. We've got inverse sine of y is equal to x plus a constant. They're all fairly easily handled, assuming it's a function we know. That brings us to this, the logistic equation. The standard one, solution of this particular function. d dx of some function is equal to some function of x times 1 minus that function. So that's your standard logistic equation. Now, we're really only going to see ones like this. So dy dx is ky p minus y. When you look at it, it's essentially the same thing. I'm just using y instead of function x. But we're going to see it written like that rather than that. So let's solve that particular one. Dy dx is equal to y outside of 1 minus y. I'm going to have some initial conditions there. When x is 0, y is a. Let's look at the slope field. There's the slope field for it, and we can see that we would end up with 3 possible ones depending on the value of a. And we've got these horizontal asymptotes that are in there, which they won't cross. So if a is greater than 1, we end up above that first one. If it's in between 0 and 1, we get this interesting shape. And then down the bottom, we have where a is less than 0. So there are 3 different solutions we could have depending on the value of a. And there are 2 trivial cases, the horizontal lines, where the asymptotes are for these particular shapes. So actually, we've got 5 solutions. So let's find them. Dy dx is y outside of 1 minus y. Separate the variables, and this is what we're solving. Well, the right-hand side's nice and easy. 0 to x of dx is just x. Left-hand side, break it up into its partial fractions. We've got 1 over y plus 1 over 1 minus y. That will integrate to give the log of y on 1 minus y. Substitute in, we have our answer. But let's make y the subject. Let's see if we can't draw out these solutions. So e to the x will be the absolute value of all of that. A e to the x will be 1 on 1 minus y, where the absolute value of a is a on 1 minus a. And eventually, there we have it. Y is equal to a e to the x on 1 plus a e to the x. Notice it's a different a. I've got a capital A as opposed to the little a. But my capital A, as I say over there, is a on 1 minus a. Well, I'm going to rewrite that. I'm going to make it b. B is going to be the reciprocal of this capital A, and we get a much neater answer. I've also divided top and bottom by e to the x. So I get 1 on b e to the negative x plus 1. There are my 3 answers, which will end up being 5 answers depending on the value of b. We have the 2 trivial solutions, but we also have y equals 1 on b e to the minus x plus 1. Find any inflection points in the logistic curve. Okay, well, we know possible inflection points will occur when the second derivative is equal to 0. The second derivative is the derivative of the first derivative, and we know the first derivative is y times 1 minus y. So we're now differentiating that with respect to x. So I've got to do it implicitly. I can't do it with respect to x, but I can do it with respect to y, and then multiply that by dy dx. So differentiate with respect to y, write down the first, y, diff the second would be negative 1, so I've got negative y, plus write down the second, 1 minus y, diff the first is 1, and dy dx we know is y outside of 1 minus y. Putting that all together, we now have y, 1 minus 2y, 1 minus y. We end up with 3 possibilities. However, only one of those could be an inflection point, because remember, y equals 0 and y equals 1 were the 2 trivial solutions. They were horizontal lines. There's no inflection point on a horizontal line. So the only possible inflection point is when y is equal to a half. So we have our possibility. So all right, we found the possible y value. Let's go now find the possible x value that goes with it. So b e to the negative x is 1, e to the x is b, x is log b, and if we trace back, b is actually the absolute value of 1 minus a over a. I can use the slope field to confirm. So I don't have to do any more calculus. I've been presented with a slope field, so I know there is a change in concavity. We can see from the picture, there it is. There is a change in concavity. So yes, it is a point of inflection at the log of the absolute value of 1 minus a half, and that is our logistic equation. Enjoy that one. I know you will.